Very good. We'll go ahead and get started. Well, hello everyone. Thank you for taking times out of your busy schedule today to learn a bit more about AC mitigation and some of the many new ways for automating and aggregating data to do so. I'm Nick Rendell with Technical Toolboxes. On the line today, we have Kirat from Cenozon, who's product manager there, as well as Joe Pikas on the Technical Toolboxes side, who's one of our longtime experts in really all things pipelines, but especially focused on corrosion and AC mitigation. With that today, I will pass over to Kirat in just a moment. I first wanted to highlight, if you do have questions throughout the event, there is a question pane on the Q&A on the side panel. Please put your question in there if you have one, and we will have ample time at the end to go through those in the order they came in. With that, I will pass over to Kirat, and we'll go from there. Thank you.
Good morning, everyone. Thanks, Nick. Myself, I'm Kirat Purohit. I'm product manager at Cenozon. Been with the company for about 15 years, and my background is in mathematics and data science. My passion has been everything data, more specifically, everything spatial data or geospatial. And you'll see a bit of that in the presentation today. So today we're going to be discussing our integrated gateway, more specifically asset connectivity within that gateway or within that integration, and then more specifically on data requirements for AC mitigation and workflows, so mapping data, soil data, ILI data, and then Joe, the SME for AC mitigation, will be talking about induced voltages and mitigation, faults and results, inline inspection and how that relates to AC mitigation, and then we'll have a brief summary and a discussion on the benefits, and as Nick mentioned, a Q&A period for any questions that come out of today's discussion. Apologies in advance, I've got a little bit of a sore throat, so hopefully I can make it through without coughing in everyone's ear. So around the integrated gateway. So I'm not going to get into too much detail, but this is basically Cenozon's platform, and at the core of it is asset connectivity. And what we do and what we pride ourselves on is bringing together a variety of different systems that relate to pipeline or pipeline operations, everything from the wellhead to your facilities, your tanks, your separators, every critical asset related to your operations. And through various applications, we bring all this data together in our platform. The solution that we offer is completely cloud-based, it's scalable, secure, it's real-time in most cases. We do that through our partnership with Azure. We have APIs, so the data that we're bringing in and bringing into the platform, you can pull out however you need to. It's your data at the end of the day. We do integrations with other systems, such as SAP or Maximo, other work order systems. And so we're adding value to the asset connectivity modeling or platform, but also providing feedback to a host of other systems. Everything that we do, we integrate GIS. So it's not flat data. It is, in most cases, full 3D or 2D where applicable. We are partners with Esri. We do work with, we adhere to pods in most cases. So the data is structured in based on industry standards and can work with virtually every GIS system out there. We bring in third-party services such as data lakes or other integrations that like BI tools, Power BI, etc. in our gateway, and we also bring in other third-party computing data, SCADA data. All of this is done in real time. And the goal here is not to copy data from one place into another, but is actually to what we call DVA. So digitize your operations, visualize your operations, and actually associate them together. So we're not just copying spreadsheets and other data tables just into another database. We actually bring in business understanding of your operations, and tie these things together. And I'll share a few examples of that in a few slides. At the core of this, again, is our asset connectivity. So getting a little deeper into that, ultimately it provides insights on your pipeline networks, your operations, specifically around pipelines or around reliability, maintenance, risks, inspections, etc. So we bring all of this data from disparate systems. It's supported by a whole host of integrations and GIS data, SCADA data, etc. And ultimately, we tie it together to provide you insights for further understanding of your operations. Asset connectivity. So again, at the center of the diagram here, we've got an example of a pipeline operation. So from wellhead to separator to storage tank to other facilities, to your sales lines, etc. At the top of the diagram are examples of the type of data we're talking about. So your pipelines, all the characteristics of your pipelines, materials, grades, etc. Your wells, where your facilities are. We bring in a bunch of public data, so elevation models, survey systems, roads, rivers, creeks, HCAs. All of that comes in an automated way. So all of these data sets we schedule, we've integrated with virtually every field data capture system. We will work if you have private systems to build those integrations. But our goal is never for you to have to export data, import data. All that happens in the background and as real time as needed. We'll bring in SCADA data, sampling and analysis of your gas and water samples, ILI data, excuse me, coupon data, other inspections, and then other supporting information. So if you have surveys, photos, videos, so all of this data we bring in an automated fashion. And then we have a whole host of applications to support visualizing the data, adding value, risk assessments, providing insights, or for example, for ILI data analysis, run-to-run matching, and analysis on your inspection data, as well as mobile apps to help collect this data if we don't already have it in a digital format. So actually creating your digital twin, and all of this feeds into our asset connectivity engine. And the other thing we do pride ourselves on is that this data is available to all of your other systems. And so if you're working with work order systems, Maximo, SAP, other databases, your BI tools, and for today's demo, we're talking about Technical Toolbox, so we'll also integrate with Technical Toolbox for you to further analyze and gain insights on your information. So around AC mitigation, there's a lot of underlying data that is required to conduct that study and understanding of where your risks are with relation to AC interference. So examples of that would be your pipeline central line, so knowing where your pipeline is. Depth of cover or topography is important, whether or not there's road or water crossings. Understanding the nature of soil, where the power lines are and the nature of the power lines and towers within proximity of your operations. With this GIS data, we offer pretty much automated pre-processing of the data. So dynamic pipeline segmentation, we'll see, can be dynamic or can be user specified. So in the case of fixed length segmentation, you may want to sub-segment or segment your pipelines based on some static values for every 100 feet or 50 feet, whatever is relevant for that project or for that pipeline, whether or not there's road or water crossings, or based on some other user-defined criteria. Soil classifications, so based on your pipeline centerline and soil data, we can actually automatically classify these segments as to, for example, what the conductivity or resistivity for that particular pipeline segment is in contact with. We'll do elevation and pipeline profiling, either based on if we have IMU data or survey data for that pipeline. We can use that, or we can use general DEM data or elevation data from other private or public sources. And of course, the results will vary based on the type of data, as well as power line and tower locations. So we have a host of public data sets available, and we can also accommodate any private data sets that are provided by your local power company. Our connectivity engine, which I'll briefly touch on, allows you to identify where you currently have, where your current mitigation efforts are. So where you might have your anodes, exactly on what pipelines and their location, or what segment they're located on, any wires or cables, and bonding to other pipelines. So we can identify that in our connectivity model, either in an automated way or on a per project basis. And that allows for feeding that data into the risk algorithm for current and future needs. We also host ILI data, and this would be the raw data coming from the tool or from the vendor reports. We import the data. It's a completely agnostic import process where we do quality control to make sure the data makes sense. We'll do the linear referencing on the central lines where we need to if we don't have IMU data. And we can even do run-to-run comparisons for short-term and long-term corrosion growth rates. And of course, through the data, we can identify where all our welds and casings and valves and other critical features are located. And then this obviously would feed into the risk algorithm, specifically around the AC interference. So there's a lot of data, and if you look at the screen, just gathering the data could be a challenge, especially if you wanted to do it in, on a larger scale. This could be a challenge, and then trying to repeat the process again can be a challenge for further analysis. So what we do, again, our systems are full 3D enabled. So this is just an example of a pipeline centerline. It actually came from an ILI in this example, 24-inch line in Pine River in Northwest BC, Canada. And so we'll provide the GIS data in our system, and through that, if we have IMU data, we can use that as far as its elevation or depth of cover. And if not, we can use public data public or other DEM data sets to derive topography. There's a host of public data sets for power lines and towers. You have to kind of take them with a grain of salt as far as quality, but we can also look at or integrate with other private data sets, other from your local power company, or other public domains. And then we also do analysis as far as, or proximity analysis to roads or rivers or other HCA areas. So an example of this line crossing a river, and based on its location, again, the dynamic segmentation can come into place based on proximity to HCA zones or water road crossings. Survey data, so we do host soil surveys in our system as well. So the type of survey, and I guess more specifically, conductivity, resistivity. We've also worked with USGS data, and again, at a macro level, quality is decent, but at a micro level may not be suitable. And we've also worked with other commercial soil survey data sets, typically through direct assessment and for a particular project. But all of this, again, we integrate in our system, and it gets tied back to the pipeline and those sub-segments that we're interested in. Other types of GIS pre-processing. So again, the dynamic segmentation. This is an example of I guess a 37 mile or kilometer pipeline. I have to double check. And so we've segmented based on, in this case, was based on the location of ESDs. I believe this line crosses 8 or 9 different creeks or small rivers. And the client, in this case, wanted to identify their risks and other susceptibilities based on the location or the pipe segments between these ESDs. Other clients might be interested in segments that are crossing these HCAs or road or water crossing sites, or there could be dynamic segmentation or segmentation based on changes in diameters or coating type, etc. For each one of these segments, we'll do the soil classification, type, depth, the profile, which you can see on the screen here, as well as proximity to the power line and towers. Post-processing, again, I'll let Joe talk about for a little further, but would include the AC mitigation studies, how that impacts risk, overall risk assessment, and then again, how ILI data applies to the AC mitigation study. This is an example of our connectivity engine, or a visual of our connectivity engine. And in this example, we've got on the right a pipeline 34056, and between these two sites, you can see other pipelines tying in. But we've identified where we've got anodes at that 4 of 25 location, as well as any cables. So this is how we would associate, I guess, these mitigation efforts and how they would relate to each pipeline segment. ILI data, as I mentioned, we do support hosting or analysis, import, hosting, and analysis of your ILI inspections. And an example of the future distribution along this particular pipeline with respect to internal and external defects that were identified in the inspection. And then, of course, we'll also be able to identify where we've got metal loss, valves, optics, welds, etc. through this data. And this, again, gets tied back to that pipeline segment through our connectivity engine. With that, I'll pass it off to Joe, who's going to dig a little deeper in how this data supports AC mitigation.
Well, thank you, Kirat. And you could advance the slides as I go along. I don't have control here, so I'll let you do that. Mitigation of induced AC voltages. You know, one of the things that we just heard is about the data gathering. And there is a lot of data gathered. And one of the things is we're looking for ways to make it simpler. You know, there's many places that you could get links to the power companies, but they only give you the voltage. It's 220, 250, whatever it is, 345, but they don't give you the loads. And then with the climate change that we've had this past summer, particularly in Texas, and we still haven't seen fall yet. I'm waiting it to fall for fall, but we're, you know, the power loads have gone up significantly. Example, we'd get newscasts that the temperatures, they give us a warning from 9 a.m. to 10 p.m. We're in a heat advisory. That's all day. That's the entire daylight time. And that's pretty significant. So you could see loading plays a real important role. And here's a power line, this blue line. And many things have changed where we used to have maybe a 5 or 6 hour duration of peak loads. Now we're experiencing 12 or more hours of peak loads during the day and even night. It takes, you know, even the nighttime temperatures are pretty high. Midnight, still 90 degrees. And so just to give you an idea, and that's not considered a part of the heat wave. So give you an example of what we're dealing with. So we need to have a lot of information. We need to know what the shield wires are and what are the shield wires for lightning and things of this nature, for episodic upsets and things of this nature for the power companies. What about the phase wires? You know, the depth, the height, you know, what they are, you know, what angles are they? You know, how are the load? How are the how they placed? Are they any changes? And going on. And I mentioned the loading. You know, that has been significant. Are we calculating? Are we considering the peak loads duration now? You know, we had 5-6 hours a day. Now we're doubling that for the summer. So we need to think about those kind of things. What about the power line types, and so on? And then of course companies are uprating their systems just like pipelines, the power companies, and they'll increase the voltages to transmit more power, and that not necessarily the current. It'll go up proportionally, obviously, but the whole point is we need to keep on top of what's going on. Like Kirat says, we have, you know, we could get the data in different ways publicly, but what about getting the actual data? You know, and we could do estimates, and sometimes we have to do that, you know, based on availability of data. So if we need to get down and dirty into all the details, sometimes we have to do an estimate. The pipelines, we need to know the diameter, cover, coating resistance, coating thickness, and where the isolating flanges are. So I just want to point something out in this map, this ArcGIS map. This is the compressor station. It's located in a mountainous area, and right where you see this discrete anode is an isolating flange. And what do we have across that isolating flange? Well, we have a decoupler, and that's why it's a discrete, because it's draining current back to the station. And we know we have some problems in this area. Why? Because we have a change in direction, or the point of intersection where the power line enters the pipeline right away, or vice versa, whoever's in control. So these are the kind of things. So we did parallel placement wire in this location, and you can see these section lines. And why do we draw section lines? Is because we could identify where the power lines are located, the towers. We could identify where the point of intersections are. We could identify the changes. We could identify soil resistivity changes, or anything that's related to that would cause an increase or a decrease in induced voltages. So this is one of the reasons why this system is there, because we could actually see the terrain, we could see what's going on, and we could actually get a better assessment by the placement of section lines, also to determine where our mitigation begins and ends too. So it's another reason. And we could shorten it or lengthen it based on the section lines or whatever, or add them up. So we have all these ways to look at things. So I put in 3 different types, and I put the distributed anode system because as we're going away, we just don't need quite as much don't have much of an issue here. So the heavy duty stuff is in this area here, where where the issues are. So when we have mitigation of AC, the engineer or user makes these determinations. In other words, it's not just generated. There's some actual thinking behind it. What type of anodes to use, whether it's a distributed system, whether it's a parallel replacement wire, or maybe both. We have situations where sometimes you have to use everything because of the type of problems that induce voltages and currents that are modeled. And then of course discrete, and that's usually a deep anode system, but you could use it other ways too. And then bonds to other pipes and things of this nature. And the other thing we look at too is the soil resistivity. Whether it's there's all different layers, but really when it comes down to it, there's 3 major layers. It's the layer around the pipe, which I'm going to call it the corrosion layer. And why? Because that's where it happens. That's where the current density. That's where the current density is. Then we got our surface, where we could have conductive faults and things of this nature, and then we have the deep layer where the inductive voltages are usually measured, and that could vary anywhere from typically it's about 30 meters in depth. To get a better assessment. Next slide, please. Okay, thank you. AC faults. That's a big problem. And where do they usually occur? Well, it's pretty simple. The closest tower or pole or to the pipeline. That's typically. Well, the software can calculate them all if you want. If you want to look at every one or the closest or closest, you could do that. And this is the nice thing about having software that has the capability to model what you need to be looking at. That doesn't mean lightning is going to hit that area all the time. That could be a low area in a mountainous area. And as we all know, anything on top of the mountain gets nailed. So this may not be the area of concern, but you could put the type, make the assessment the way you want to see it, from all of them to specific ones. Just want to let you know. And we need to know, what's going on, the type of towers they are. And the episodic upsets that occur, due to either storms or the changes in the system itself due to other issues, or vandalism or terrorism. We need to think about those things. And then we look at average resistance of the tower to ground and tower separation, closest distance to the tower, and so on, so forth. And as I mentioned, all towers. And the graphical results are pretty evident. What we look at is the coding voltage, and you could see that we did some mitigation in here. And if you look really close at the map, you see this dashed blue line. And what that was done for was the idea that based on the proximity of this tower, it was decided that the arc distance was very close to where conductive fault could occur. Not that it's going to happen, but should it occur, you could do individual types of mitigation for faults as well as for AC. You could separate them out if necessary. The other thing I want to talk about is the surface potential rise, that what we're talking, and the step potential and things of this nature, and the touch potential. So we have all those things to consider. Typically, the step, touch, and surface are usually related to any above ground appurtenances, such as a valve, a riser, or anything like that, where someone could touch it, and there's a high likelihood of getting shocked if the appropriate grounding grids are not put around it. Next slide, please. Okay, we mentioned risk algorithm, and what we have is a simple matrix here, and one of the things, the regulators, what side of the border you're on, I don't care, or what country you live in, there's concern about, are you susceptible to AC interference? Well, remember I said that the pipe is the corrosion layer, what's that? Usually about a meter, maybe less than a meter, or just over 3 feet, is the key. And of course, it's still susceptible to wet and dry cycles. So soil resistivity does change with seasonal variations, with flooding and things of this nature, other issues. But we could look at where the pipe would be susceptible with simple calculations. USDA has data, and it's just about it's just at the limit of what the pipes are just buried at. But the point is you could do some nice studies on some of this stuff and get a preliminary assessment. Hey, we got these towers here, and we know that they are pretty big, whatever they are. Let's just say a 500 or 750 kV. That's something to worry about. System, and you could easily come up with a simple matrix system to say we are susceptible to AC interference based on a 1 square centimeter holiday, and that is the criteria. And if you look at some of these voltages here, I had a question asked the other day. They said, what if we're in a brackish river water, and the resistivity of that brackish water is around 30 or 40 ohms centimeter? Well, that's down here. Okay, that's below 100. Okay, this is 1 volt. You could have a 1/4 of a volt and have AC corrosion. Yes, we have a problem. Conversely, if you look at something, 1 volt, say 300 That's not much soil resistivity. You don't really get into anything until until you get up a little bit further. You know what, 1,000 ohm centimeter, or above, and then the voltage has really got to go up before you have any kind of a problem. So if you're sitting at 50,000 ohm centimeter, not an issue. If you're sitting at 10 million ohm centimeter, the likelihood will be almost nothing. But then that's a desert area. But at the same time, in that same desert area, you come in and you got a saltwater table, then all of a sudden comes up, and it's 30 ohm centimeter. So you could go from 8 or 9 million ohm centimeter down to 30 very quickly, and then you wonder what happened. So it depends on the environment you're working in, and knowing what those soils are, and having the right soil charts, whether they're public or whether they're derived from other studies. That's going to cost some money. Is very important. So resistivity plays a role, but you could also use some basic information just to get a pre-assessment of, is there a likelihood of metal loss? Is there a likelihood of high current densities on this line? Another example is several companies, and they know who they are. Within 6 months of installing a pipeline, they already had leaks. So that gives you a clue of the rate of corrosion that occur, and they're not big, large holidays or deep pits. They're very small, but the problem is they're steep and deep, and that's what usually occurs because it's so focused, that current density. Next slide, please. ILI feedback. We mentioned ILI earlier, and I got a really neat story to tell you. The story is companies years ago were basing all of their mitigation on where the pitting was. It was after the fact. An ILI run is after the fact. It's not pre-screening. It's too late. The metal loss has already occurred. And they were basing on, well, we could catch up on it if we do it every year. Well, what happens? So I'm going to show you a little story coming up right after I go through this about several companies have done. They chase the metal loss, due to AC corrosion, and only mitigated those areas. And I have a nice little story to show you how important that is, and to model, and what happens when you don't model. And this has happened to several companies because you have to, because it's ongoing. It's a continuum, and we can't stop. If you're going to do something like that, and particularly in today's world of high loadings on the towers, we don't have a choice on some of this. What used to be 5 or 10 volts now is up to 60, 70 volts on some of these pipelines. That's pretty significant. And so we'll talk about that. So level 1 is a process that screens for potential problems that can reduce the time required to understand where more effort or focus is needed. Okay, we're talking about an AC mitigation modeling program. ILI runs, use unity plots, and which are typical, and the unit slope band is the predictive model is created by a known corrosion rate to predict the existing corroded areas in the last ILI run. The results of the model are compared, to the ACPT. Level 2 is a process that requires feedback. So what did we learn? Okay, and I'll show you that. Analysis, like engineering the most effective mitigation. So that's another thing. Is our mitigation that we put in, is it working? And the cycle continues until the life cycle of the pipe and knowing when the next assessment is needed and will be key to optimizing the balancing act of controlling maintenance costs while delivering a promise of flow insurance integrity of the pipeline. So there is a fine balance in there. Next slide. Okay, so here's an example. Okay, and this really happened. There was a company that decided to, they had an ILI run, and they found all their metal loss in this area from milepost 2.5 to 4.0 or so. Okay, so they said let's just mitigate this whole area. We don't care. We don't want to see any modeling. We're going to just take care of this. Well, the non-mitigated area, looked pretty good, except for a few areas over here. But other than that, the steady state AC and AC current density ILI plot shows only half the picture. No mitigation was planned in the first 2.5 miles. None. Now, nobody did any modeling till later. Okay. But anyway, next slide. Let's go to the next slide, and we'll see what happened. Okay. So what happened was they decided to do modeling about 10, 12 years later. Okay. And so what happened? Okay. What happened was this area was really taken care of. The current density is way down like it was supposed to be. Okay. But look what happened for 10 to 12 years later. They didn't look at it until someone modeled it later. And this is the non-mitigation area. This was based on the ILI run of the anomalies that they found. Okay, so the mitigation went in, but nothing was looked at here. And when you're looking at a short section of line or a small lateral, that's a big deal, because what you do on one end, guess what happens to the other end? It's like a balloon. You press down on one side and the other side goes up. That's exactly what happened. And so here we are. Now it shows a higher induced voltage and current densities after the ILI anomaly area was mitigated. We don't want to be running like that. We want to do both. This is what it's about. It's about verification and where the modeling and the ILI runs are done consecutively, so they're tracking each other. We can't let something like this go because and not track it. And this is one of the things where we get in trouble. And so this is why I brought this out. And there was a bunch of companies that had took that philosophy, but it's not a good philosophy, because what we need to do is it's a continuous process. It doesn't end because you mitigate it in one area. Next slide. So when you model, okay, and then take care of the other side, okay, now we have a different story, okay. Now it looks like we've got something under control, where instead of running 60, 70 volts, we got it down to 3 or 4 volts. We got the current density pretty, not quite, less than 30 amps per meter squared, but 30 amps per meter squared is very conservative. It's based on 1 amp that you have at least 1 amp per meter squared DC on your pipeline. If you got 1 amp amp per meter squared DC, that you're over polarizing the pipe. That's a lot of cathodic protection. So anyway, I wanted to show this plot to show when you bring the two together, this is what it's about. You can call it aggregation of data. You can call it integration of data. You can call it digitization of data. Call it what you want. But the key is when you bring it all together and aggregate it and using ARC GIS systems. Next slide, please. When you bring this connectivity together, combined with ArcGIS and dynamic segmentation, provides the user a complete experience when integrated, with the AC Power Tool. What we're saying is doing half of it is doesn't cut it. Whether you just model or whether you just chase the anomalies, neither one works by itself. You have to do both. And what we're saying is the core features allow the user to do pre and post processes, for difficult data to visualize. Because when you're looking at something like Kirat showed with all that corrosion on an ILI run, it was like contiguous all the way through. I mean, they lost their way on that one. And so what I could say is we could link all this together and bring it in while leveraging the power of the geospatial analysis tools. When combined with public and commercial data sets, we could look at some other things and look ahead, particularly companies with larger pipelines or more power lines coming into their right of way and so on and so forth. So we know what's going on, even if it's just a pre-assessment, to see, is there a likelihood of this occurring? Yes or no? And we could even get even an assessment of how bad it's going to be based on the tower voltages and things of this nature and the load factors. So the pros of a GIS Simple is a simple interface that is compatible with all major pipeline data sets. Next slide, please. Okay, so continuing, ArcGIS mapping allows the user not only to run the ACPT modeling, but also the soil resistivity layer studies. You could get down deep in those if you need to. Risk assessment, integrity, ILI metal loss, and other studies that were previously unavailable. With the layers, the map layers and things of this nature, when we start bringing these layers in, we get a better understanding than we've had before. And not just doing a pre-assessment, we need to do a post-assessment on it too. And therefore, meeting your customer needs or your own needs, you can meet the regulatory deadlines that are required while providing, here's the key, the integrity of the pipeline, not letting it get it out of hand. And there's justification for this. Next slide, please. So to bring all this kind of together, map, model, mitigate. This is what we're talking about. We're talking about integrity. Yes, it's AC. Okay, could be anything, but for this discussion, it's AC. We could uncover existing hidden sources of corrosion. We can't get it all. The pig run is not infallible. It's fallible because we still have people looking at it, and usually the pitting that you see is small. It's not like large lengths of pitting. AC are small leakers, and that's the problem, and it's easy to miss. And we could look at minimize AC corrosion mitigation engineering times and costs. We could identify the potential risk issues and design mitigation without even going to the field. In the end, you need to get to the field, but I'm just saying we could do some identification before we start and focus on how to budget and do things of that nature. And then analyze the heavy AC power line concentrations in HCA's. Example, 12 pipelines and 12 power lines that could easily be handled. Integrate GIS mapping with ILI and risk assessment to make better critical engineering decisions. This is what the regulators are telling us. Hey, how are you guys going to handle this? Do you have the right information? This is what it's about. And how about a plan? We could come up with plans a lot faster with rapid modeling iterations. You know, we could do the what if and what as and whatever ways you want to look at it. And then, of course, it works for both new and existing pipelines. And with that, I think we have a question coming up.
Can we go back to the prior slide, Kirat, please? Very good. Okay, so just logistically here, folks, everyone that attended today will get this copy of this recording in the next 48 hours. We do want to just kind of help steer our, our follow-up and our additional resources. So there's gonna be a poll that pops up on the screen here. And just if you do select you want more information about Cenozon or the AC Mit PowerTool on our side, please let us know. If you want information about both, great. If you want information on neither, great. You will definitely not get any additional emails or phone calls, and that's fine too. This just kind of helps us. So we'll give you 15 seconds here, and then we've got the questions rolling in, and we will use the rest of the hour to talk questions. So thank you very much. Very good. And with that, let's move on into questions. The first one, I believe, is for you, Joe. So this was sent during the AC Mit part. So the question is this an iterative model? Can you rerun the model later if some assumptions or unknown items are found out to be wrong? Or would you need to input new loads?
Yes, you could do iterative modeling. Yes, this is what it's designed to do. And you don't have to keep unless there's changes, obviously, if something occurred during the last study, you'd want to update that, but that's all you'd have to do.
Okay, next question, I believe is for Kirat, but Joe, feel free to chime in as well. The question is around input factors and results. So how easily is everything transferred in and out between the systems and to different users and clients around the org?
So I mean, great question. Our goal is a fully automated way, either through direct integration, so like web APIs, and again as real time as needed. And I don't like the word easily, but our goal is to, again, create those integrations. And ultimately the data, providing that data to other systems to add value is, 1 + 1 doesn't have to equal 2. And so, yeah, we, through our reporting APIs or data APIs in our gateway, that's all facilitated for any of the data that comes in and transferred out to other systems.
Okay, Joe, anything to add on your side?
No, I think this is where the strength of this system comes in. Is what Kirat has said is the ability to take what has already been looked at, and then looked at it, and then go through another process, and then re-looked at again. And this is where we uncover things that sometimes we didn't see the first time. And this is the importance of it. Sometimes we miss the obvious.
Very good. Okay. Next question. Do you account for frozen conditions like those found in Western Canada for soil resistivity? This is all based on summer measured soil resistivity. And if so, how many soil layers does the modeling account for as an output? Joe, that's a question for you, I think.
Excuse me. I think I got what Kirat had. but we're on different sides of the border. Okay. Anyway, what I wanted to say was, obviously, soil resistivity is such a controversial subject. We could open a 50-hour discussion just on soil resistivity. And the thing of it is, you know, obviously, when you're dealing with frozen ground, that's a whole new ball game. You know, it's similar to what you're dealing with seasonal variations where the ground is dried out, and you go from let's just say you go from a 1,000 ohm centimeter down to literally, or you go up and you could go up to 50,000 because of dry soil. You know, there's no moisture. Moisture plays a role, and this is what we're talking about. And will we ever get the right amount of moisture? You could be saturated, less saturated. You know, it's just like anything. So what we have to do is you know, make a decision on the soils that are going to cause the highest rate of corrosion. We don't have a choice, and it's all over the place. And making that right decision, I know people spend a lot of money on how many layers there are and everything else. I mean, you could take it to the nth degree, but in the end, it's that pipeline with that type of coating that's in contact, you know, with that soil at the time, you know, when that we have to calculate, you know, the worst condition, because that's all we could do, and you could vary that number from whatever you want, but you've got to make a you know, a decision on what it is. And I know there's a lot of controversy out there. You know, we do curve fitting and we do this and this method's better than that. And we want to do 100 layers versus 3 layers. I'm not going to get into that because you could discuss that to the cows come home. But the bottom line is the pipe is in the corrosion layer, wherever that layer is. And that's what we need to focus on. And that's one of the things that we need to decide. Yes, and it's going to have this percent moisture content and et cetera, and that will give us the best assessment we could get. Will it be perfect? There is none. It's not going to be perfect.
Very good. And here's the last question, and I'll just go ahead and answer this one as we're out of time. But the question is, can we buy your software and implement the system on our own to perform AC mitigation modeling? And the short answer is definitely yes. I would say if you are new with the software, of course, we've got plenty of resources on our side, you know, Joe Pikas being one, to make sure that you're using it correctly, you know, within your org. So very good. Well, with that, thank you all for the webinar today and your attendance. And like I said, expect the recording here in the next 48 hours, and we can follow up any additional questions you have from there. Thanks, and have a good day.
Thank you.